My name is Eli Goldweber from the University of Michigan, and today I'm going to be talking about the importance of testing specifications, and specifically how we achieve this by building IronSpec, a specification testing framework that we successfully applied to identify 10 specification bugs across the specs of 6 open source verified systems. When verifying systems, developers start by capturing the properties that they wish their systems to maintain in a trusted spec. These act upon as the pillars upon which the guarantees of verification are built. Together with any implementation and proof annotations, a developer can pass these 3 ingredients to a verifier. The verifier may reject the proof, but if the proof passes, that gives clear indication that the implementation maintains all of the properties defined in the specification. More specifically, what this means is that with a passing proof, all of the reachable behaviors of the implementation are within the subset of the allowed executions defined by the specification. And verification is attractive for exactly these strong guarantees. Aided by recent advances in automation, the adoption of verification is only increasing. But the guarantees we get when we verify our systems are only ever as strong as the specifications. If there is a bug in the specification, there could also exist a bug in the implementation, even in the presence of a passing proof. This can occur if the specification is weak enough such that it allows for some buggy behavior. A developer may then write an implementation that is also buggy, and they may also arrive at a passing proof, falsely giving the illusion of correctness even though their implementation contains a bug. A developer would need some way to identify this as the case, strengthen their specification to remove the previously allowed buggy behavior. This would inevitably result in the proof failing because their implementation is no longer a subset of the spec, so they would also have to revise their implementation and fix their proof until it again passes. Current techniques to ensure that specifications remain bug-free and avoid this exact case rely on manual inspection and system expertise, with the insight being that specifications are typically small enough and understood well enough to make this task feasible. But we find that even experts make mistakes. This is an example of a double spending vulnerability in a verified Ethereum smart contract that was initially missed because of a bug in its spec. But also prior work have been able to successfully identify bugs in specifications, but have mostly relied on manual effort to do so. As the adoption of verification is increasing and more non-experts are writing specifications, it's all the more imperative that we make this process as robust as possible to ensure that we're proving the correct properties about our systems. Now, we don't want to only rely on manual effort to ensure that our specifications are correct, and we don't want to trust that our specifications are correct. But on the other end of the spectrum, we can't prove our specs correct either. If we try to prove our spec correct, we would need to prove it against some property, and we would have to write down a spec for that, which essentially is just reintroducing the problem that we're trying to solve in the first place. And we could keep doing this circularly, and we would have the same problem over and over again. So to tackle this, we aim to help increase our reliability in our specifications by testing them. We show that we can increase our ability to identify spec bugs by adapting techniques used to test traditional software systems to test our specifications. We do this by building IronSpec, which is a specification testing framework that combines both automated testing techniques as well as a manual testing methodology to help achieve this vision. Before discussing about the details of IronSpec, let's take a look at an example of a specification to get some insight to the subtlety of this problem. Consider a specification for sort. Here we have a method that takes an input sequence of integers and returns an output sequence of integers. The specification is a single post condition that stipulates that the output be ordered in ascending order. At first glance, this may appear to be a correct spec for sort, but it's in fact incorrect, a mistake that we find many newcomers to verification make. It's in fact too weak because it does not constrain the values of the input in relation to the output. A verified implementation for this method might be free to return any output sequence as long as that output is ordered in ascending order. We can see this more concretely with some specific values. We might choose to sanity check our spec with some specific input-output pairs. And given some arbitrary input-output pair, we might find that this is allowed by our spec because the output is still ordered in ascending order. And it matches our intent for what it means for sort to be correct. But we may quickly arrive at a counterexample where, given some input sequence, our output sequence contains none of the values originally contained in our input, but it's still ordered in ascending order, so our specification would allow this. But it contradicts with our understanding of what it means for sort to be correct. This is allowed because our specification is too weak, and it allows for this buggy behavior. A developer would need some way to identify this as the case and then strengthen their specification to remove the previously allowed buggy behavior. They might do so by adding an additional expression stipulating that the multiset of the input be equal to the multiset of the output. And with this stronger specification, the previous counterexample is no longer allowed by our spec, which matches our understanding of what it means for sort to be correct. When testing or debugging a specification, we leverage the notion that specification bugs, like any bug, occurs because of a disconnect of intent. There's a disconnect between what's intended in the specification and what's currently captured. Note that because specifications are often meant to be abstract, they may allow for some additional benign behavior. This behavior wouldn't lead to a violation of safety. But if there is a specification bug, it occurs in this disconnect. And so we design IronSpec with this in mind to provide tools and techniques for developers to identify these potential areas of disconnect, which in turn helps to streamline the testing process by narrowing the scope of the specification that's necessary for them to actually spend the additional effort to test. For the rest of the presentation, I'll go through the components of IronSpec, an automatic sanity checker, a manual methodology for writing spec testing proofs, and an automatic mutation testing framework to describe how these help us identify these disconnects and how they work in tandem with one another to let us test specifications. Starting with the sanity checker, this is a tool that flags common cases of disconnect between the input and output of a verified method and its spec. We can see this with an example. Consider a method bar where this method takes an input of an integer, x, and returns an output of type f, which is a data type containing multiple fields. In this example, there's no post condition constraining the output at all. So an implementation for this method might be free to return any arbitrary value of type f. Now, in most cases, this would be considered a specification weakness bug. And so this complete disconnect between the output and the spec is able to be flagged with high confidence of the existence of a spec bug. But a developer may update their method and add some expression for their post condition, constraining part of their output. In this case, some of the fields of the output data type are still left unconstrained. And the sanity checker is still able to flag this as a partial disconnect, alerting the developer to this potential specification weakness bug, but still requires the developer to answer that final question of whether or not that's intended or not. We can apply the same sanity checking to our 2-week sort specification from earlier. We can see that the output sequence is constrained by our specification, and every index in our output sequence is constrained in some way. But we would quickly identify that the input sequence is completely disconnected from the specification, which is actually the reason why we saw that counterexample a few slides previously. Remember, if there is a specification bug, it occurs in this disconnect. So the flag raised by the sanity checker is alerting the developer to the existence of this possible disconnect and forces them to answer the question of whether or not that's actually intended or not. These flags leverage generic coding patterns about the specification itself, but don't help answer the questions about the context specific to the specification. So to help answer those questions, we define a methodology of writing spec testing proofs to answer those questions specific to the context of the spec. STPs, like the name suggests, are proofs, but they're proofs about a specific property of the spec. So for instance, if we were considering our 2-week sort spec from earlier, rather than just trying to sanity check this ourselves manually, following the methodology of STPs, we could be guided to write an actual proof to see if the specification allows those specific values. In the paper, we define a few types of STPs which help answer different questions about one specification, but for the sake of time, let's look a little closer at one type of STP. A correctness spec testing proof aims to help answer the question of whether or not our spec is strong enough to reject some invalid output. So like we saw before, a developer would write a proof to test specific values. In this case, they are specifying an output that is intended to be invalid. So in this case, our output should be invalid for sort because it drops the value that was originally contained in our input sequence. The proof obligation for this STP is the negation of our spec, because if this proof passes, it means that the specification is strong enough to reject this specific invalid output. If we were to try to verify this with our 2-week sort spec from earlier, we would find that the proof fails. But the failure of the proof doesn't actually tell us a definitive answer, because the proof may have failed for multiple reasons. The proof may have failed because, in general, in this work, we're targeting undecidable problems, and the verifier may not have been able to actually prove this, even though the values may actually, this property may actually hold, or these values are not, or our spec isn't actually strong enough to reject this case, and these values actually constitute a counterexample. So following the methodology that we define in the paper, the first step is to try to rule out the counterexample case. And a developer can do this by transforming the correctness STP into a counterexample STP, and in this case, they're proving the opposite. So the transform counterexample STP, the proof obligation is the specification itself. And in this case, if the proof passes, that gives a clear, concrete counterexample to the correctness of our specification. And with our 2-week sort spec from earlier, we would find that the proof succeeds, indicating exactly that. Taking a step back, so far we've introduced briefly the automatic sanity checker and the manual methodology for writing spec testing proofs. But it's interesting to note that these can be applied directly to the specification. They have no dependence on a completed proof or implementation, so it can be applied at any point in the development cycle, much akin to test-driven development. It's often worthwhile to test one specification before spending the manual effort to actually prove that their system adheres to the spec. But if this system has a passing proof, we can actually further test the specification by adapting mutation testing to be able to test our specification. For the sake of time, I will just give some high-level insights as to how we're able to achieve this, but for full details, please see the paper. To apply mutation testing to test our specifications, we start with a implementation, our spec, and a passing proof. We can then automatically mutate the specification by applying small syntactical mutations based on a set of mutation operators, and filter out the set of relevant mutations. Of the remaining mutated specifications, we can then automatically check to see if the original proof still passes. And if it does, that should give the developer pause because we've been able to automatically identify a different specification that still allowed the proof to pass. The existence of these alive mutations highlight a specific difference of behavior that was unaccounted for in the original specification. Remember, if there is a specification bug, it occurs in a disconnect, and the alive mutation encapsulates that notion by highlighting a specific and small disconnect that could be the source of a specification bug. A developer would still need to further investigate this, but they would only need to investigate the difference highlighted by the alive mutation, and they can do so by writing focused STPs. To recap, we've designed IronSpec, which is a specification testing framework that aims to help identify these disconnects of intent and help us debug our specifications. Whether it's through the generic hints provided by an automatic sanity checker, the context-specific questions that STPs help us answer, or the alive mutations that we can automatically identify through mutation testing. We've built IronSpec as an extension of Daphne to be able to test Daphne specifications, but the ideas and concepts of how to test specifications are not tied specifically to the Daphne language. We applied IronSpec to a number of in-house specifications, but in addition, for the evaluation, we applied IronSpec to a number of open source verified systems and have been able to identify 10 specification bugs across 6 of these open source verified systems. It's interesting to highlight here that the middle column of this chart indicates which component of IronSpec gave us the initial hint, which eventually led us to discover and confirm various specification bugs. The final step is always to write a counterexample, STP, but each component of IronSpec has been helpful in providing that initial hint, whether it's the generic hints of the sanity checker, the alive mutations of the mutation testing, or just by writing a suite of STPs, much like one would write a suite of unit tests. Because the guarantees of verified systems are built upon the correctness of specifications, testing specifications is a good way that we can increase our reliability that we're proving the right properties. And we've shown that these techniques work by building IronSpec, which has led to the discovery of 10 specification bugs across 6 open source verified systems. And with that, thank you everyone for listening. I'm happy to take questions.